Hello everyone. In this lecture, we analyze the heat equation in more than one space variable. This is given by u sub t is equal to a square Laplacian u, where Laplacian is given by so this is Laplacian in n dimension. So here a is a positive constant, and it's called coefficient of diffusivity. So this depends on the material where this flow of heat or temperature is studied. As far as mathematics is concerned, so we can always assume a equal to 1 by changing the variable t to tau, which is a square times. So we first concentrate on the initial value problem. IVT ut is equal to Laplacian u. So x is in Rn and t positive, with an initial condition given by a function g of x in R. So to a large extent, there is no difference between the analysis of this initial value problem for a general n with that of n equal to 1. So recall from the case n equal to 1, so this equation was derived. uh, so you please go through the portion from the first part of this PDE course where we studied this case n equal to 1 in detail, and the same procedure will be applied even for any general n. Okay, first of all, the physical situations, the equation, the heat equation. For the physical dimensions, so namely n equal to 2 and n equal to 3 is derived using the Fourier law of heat conduction. So this was derived in the first part of this course for n equal to 1, and same procedure if I apply for n equal to 2 and n equal to 3, they are physically relevant cases. Now, heat conduction. Okay. And then for n equal to 1, using some heuristic arguments, and separation of variables, and some scale invariance, and then we look for some spatial solutions. So by doing all these things, for n equal to 1, we derive, first of all, we obtained the fundamental solution. So we denote it by k. So it's a function of x and t. So this is given by 4 pi t to the minus half exponential minus x square by 4t. So this is for t positive and 0 for t less than or equal to 0. And then we derived this Fourier-Poisson formula. u of xt is equal to 4 pi t minus half c r e to the minus x minus y square by 4t and the initial condition gy d. Okay, so this can be written as, so k, so as a function of x I put a dot here and t, so this is for t positive, star g of x. So convolution of this fundamental solution of the heat equation or heat operator, and we also call it heat kernel because that appears as kernel in this integral operator. Okay. So just recall, so if f and g are, let me use f1 and f2 are functions from in general Rn to either real valued or complex valued, doesn't matter. Then we define its convolution as this integral f1 of x minus y, f2 of y dy, which is same as by change of variable. So this is f2 of x minus y, f1 of y dy, provided the integral is finite, and that is again f2 convolution f1. Okay. So now, so this was the case n equal to 1, and so what we really showed was, so this, let me call it by some equation. So this is just 1, this is 2. So you define by 2 satisfies the heat equation ut equal to Laplacian u for t positive, and it satisfies the initial condition in the uh, limiting sense, in the sense of limit. Further, if G is continuous at x naught. So this is very local result at x naught belonging to R, then limit u of xt u of xt as x tends to x naught and t tends to 0 plus is equal to g of xg. These verifications depend on some crucial properties of the heat kernel, the fundamental solution that we now list. It was explained in detail in the first part, but I'll just recall what are those important properties. Okay. So now would like to do a similar analysis for general n. So obviously we cannot use this separation of variables kind of thing. But however, if you look at the formula for the heat kernel and Fourier-Poisson formula, these two formulas extend readily to uh, higher dimensions. So for n bigger than 1, you cannot use the method of separation of variables. There is one case, I'll just remark that. So if the initial condition, initial function satisfies that g of x is equal to product of n functions of single variable. So here x is xn, then the problem can be reduced to, problem is I initial value problem. One dimensional, yes. But this is very specific, so we cannot use this for a general uh, initial function. So however, the definition of K and Fourier-Poisson formula readily extend to n bigger than 1. Okay. So now we'll define them. Okay. So fundamental solution. So now k is a function of x and t, and x varies in Rn. Okay, so this is 4 by t. So this factor remains same, but now the exponent changes. That's n by 2. Okay, the exponential minus norm x square by 4. So again, this is for t positive and 0 for t less than. Okay, so here norm x square with the standard norm, the Euclidean norm, xl square. So write this x x. And the Fourier-Poisson formula, also neat. So again, this is equation 4. So uxt. So let me write once in and now the integral is over Rn. So that is the only difference. So it's a multi-dimensional integral now. So exponential minus x minus y square by 4t g of y. Again, g is initial function dy. Okay, so this is multi-dimensional integral. Okay, though I have written only one integral here, it's integral over Rn. Okay, and this is again for t positive. So this again we can write it as convolution of k t star g x. The verification that u is indeed a solution of the heat equation, at least for some good function g, is exactly similar to the case n equal to 1. So let me just mention that as so very. So if g is a bounded function, on Rn, then u given by 4 satisfies the heat equation. So, for T positive. And again, as in the one-dimensional case, if G is continuous at x naught in Rn, then limit of u xt as x tends to x naught and t tending to 0 is equal to g of x naught. Since the initial value problem we are studying is a characteristic initial value problem, so we cannot expect. So in general, there is no uniqueness. So for the case of n equal to 1, so we exhibited for n equal to 1 the Tiknov example. Show this. So however, if we put some growth restriction on the solution, however, if we impose some growth restriction on the solution, then there is uniqueness. So for example, if the initial condition G is bounded and continuous, then among the bounded solutions, so this is the restriction now, among the bounded solutions of the initial value problem, the one given by Fourier-Poisson formula, is the only solution. Only solution. The verification of all these properties, okay, they depend on these crucial properties of the fundamental solution. So I just state them. So properties of, okay, which are used in deducing all these statements. All these statements. Okay. So let me just mention them. So K is symmetric. So this is X T is equal to K of minus X. So let me just restrict myself to X bigger than Rn and T positive. Okay. For T less than or equal to 0, it is any of 0 function. Okay. So in this region, okay, this K is a C infinity function of X. So it's infinitely differentiable both with respect to X and T variable when you restrict T to only positive values. K satisfies the heat equation. Okay, so let me stress again this, though I have stated there. And this integral of Rn over Rn K of X minus Y T dy. So any of from the first property, it is symmetric with respect to the X variable, so I can interchange that. So K of X minus Y T dx. Okay. So this is 1. Okay. So in this case, I am integrating with respect to Y variable, so this integral is 1 for all X in Rn. And in the second integral, I am integrating with respect to X variable, so this integral is 1 for all Y in Rn. And then crucial property, this one. So if you integrate not on the whole of Rn, but you just leave out a ball. Okay, so this Kx minus y t dy. So this is usually we neglect it, but since k is given by an exponential, so k is a positive function. So you just integrate this fundamental solution not on the whole space Rn, but you leave out a small ball. So you integrate over the exterior of a ball. Okay, and then this one limit as t tends to 0 plus 0 for any delta positive. Okay, and we are integrating with respect to y variable, and there is a x here, so this convergence is also and uniformly in x. So that limit, usually when you use epsilon delta definition to prove this thing, that given any epsilon, that delta does not, that delta and this delta are different, of course. This is any given delta that does not depend on x. So that's the uniformity with respect to x. So it does not depend on x. Okay, so this is a very crucial property that is used in, of course, all properties are used, but this is quite a crucial one. So if you see 4 and 5, okay, the 4 says it's the integral is 1 for all t positive. This property 5 show that if I integrate leaving a ball, then this in the limit this integral is 0. So that show that this integral is concentrated only around x. Okay, so that can again be seen from the formula for k, which is exponential here. Okay. Okay, with that I will stop here, and we continue from this in the next class. Thank you.